All right. Okay.
Okay. So I give you the.
Hi everyone. I'm here to talk about building quantum oblivious transfer from one-way functions. This is work with so this is actually a merge of two works that were done independently. The first was by Alex Grillo, Weijia Lin, Fang Song, and Vinod Vaikunthanathan. And the other is a joint work I had with James Bartosek, Andrea Coladangelo, and Fermi Ma. Both sets of authors had actually submitted a contributed talk merging our works, but the committee were kind enough to upgrade our work to an invited talk. So thanks a lot to the steering committee for having invited me to talk about this work. I also want to say that many of the slides that you will see in my talk have been borrowed from James Bartosek and some concepts from Alex Grillo's talks. They both talked about this at QIP, and they're both fantastic speakers. So let me start off by giving some sort of historical perspective into complexity at crypto. In 1995, Russell Impagliazzo suggested the existence of 5 possible worlds based on various crypto computational assumptions. In the bottom 3 of these worlds, most interesting cryptography actually breaks down, at least with respect to classical communication. On the top 2 worlds, which are the interesting ones from a cryptographic point of view, they do allow for some interesting crypto to exist. And specifically in mini-crypt, one-way functions exist. Some crypto is possible, like symmetric cryptography, commitments, digital signatures, etc. But a lot of the public key cryptography is not. Cryptomania was defined as a world where public key encryption exists. And then by extension, some researchers also interpreted this as a world where a somewhat believed to be a somewhat stronger object than public key encryption, which is oblivious transfer, also exists. And this slide, as you can see at the bottom, has been borrowed from a talk Moni Nair gave 15 years ago. And at that time, oblivious transfer was one of the strongest cryptographic primitives we knew. And so the landscape has changed quite a bit. Almost anything imaginable is possible based on oblivious transfer. May not quite be true, but it is still a very, very powerful primitive. And the reason it is so interesting is that it allows for secure computation. So now if you don't know what any of these words, one-way functions, oblivious transfer, secure computation mean, don't worry about it. I'm going to give high-level overviews of what they mean soon. So a one-way function is a function that's easy to compute in one direction, but hard to invert. So this is a function where given a random x and y computed as f on x, no polynomial time probabilistic machine can compute an inverse of y, except with negligible probability. Oblivious transfer is a primitive that allows 2 players, Alice and Bob, to obliviously transfer a secret from one to the other. So what this means is Alice, for example, has 2 secrets, S0 and S1. Bob has a choice bit B that is secret to him. Bob wants to learn S sub B, so the bth of Alice's inputs, without revealing B to Alice. And at the same time, Alice wants to make sure that Bob learns exactly one of her secrets and not both of them. So there is some sort of secrecy of both players' inputs that's required here. In more detail, security is defined by imagining a trusted third party and requiring that no party would learn more than what they would have learned had they been interacting with this trusted third party. And so what that means is this trusted third party would get S0, S1 from Alice, B from Bob, return SB to Bob. And in this situation, Alice has absolutely no information about Bob's choice with B. And at the same time, Bob has absolutely no information about S1 minus B. And this is actually even a little bit stronger. This also means that Alice's inputs S0 and S1 actually do not depend on Bob's choice bit B. And similarly, Bob's choice bit is chosen completely independently of Alice's secrets S0 and S1. So the way this is the way this ideal trusted third party helps us get a definition is we say that security against a malicious receiver means that the view of a receiver interacting with an honest Alice should be indistinguishable from the view of the receiver when interacting with the trusted third party. Now, there's clearly something off here because on the left, Bob is actually interacting and communicating, and Alice should not learn Bob's bit B. Bob should not learn Alice's input. So there is clearly some form of encrypted communication going on. And on the other hand, in the picture on the right, Bob is simply sending B in the clear to the trusted party and obtaining S sub B. So these are clearly different. And how can we say that Bob's view should be indistinguishable between them? Well, for this, there is the concept of simulation. So we say that there should exist a simulator that extracts Bob's implicit input B without knowing Alice's inputs S0, S1. And this simulator acts sort of as an interface between Bob and the trusted third party. So to Bob, it presents a view that is as if Bob were talking to Alice. On the other hand, the simulator talks to the trusted third party on behalf of Bob, sending choice bit B and obtaining the Bth secret. And the indistinguishability between these two worlds, one is the simulated world where there's a trusted third party and one is the real game. The indistinguishability between these two actually already implies all of the things I said before about security, which is that Bob does not learn S1 minus B, and Bob's choice bit B is actually independent of any of Alice's secrets. Why is that true? Because in the game on the right, this has to be the case. And we show, and the security requires that both games be indistinguishable. Security against a malicious sender, Alice, is defined similarly in that Alice's view when interacting with an honest Bob should be indistinguishable from her view when she interacts with a simulator. This simulator talks directly to a trusted party and sends some inputs, S0, S1, on behalf of Alice without knowing Bob's input B. One other subtlety that I should add, but that I'm not going to get into the details of in this talk, is not only do we require that the view of Alice remain indistinguishable between these two, the strongest definitions actually require that the view of Alice together with the output obtained by Bob remain indistinguishable between these two worlds. Okay, so I talked about all these intricacies of the definition early on, but what is important to remember going forward is that we require these simulators that interact with these parties and extract their implicit inputs. And so in the case of Bob, there should be a simulator that extracts B. And in the case of Alice, there should be a simulator that extracts S0, S1. The existence of this simulator is non-trivial to prove and to obtain, and that's actually going to form the bulk of our work. And now let me say a little bit about why Oblivious transfer is so interesting. So OT with simulation-based security that I just talked about actually suffices to obtain general purpose secure multi-party computation of arbitrary quantum functionalities. What that means is there's a set of servers that given inputs x1, x2, x3, x4 would like to compute an arbitrary function on them without revealing anything else about their private inputs. And F could in general also be a quantum circuit. And it turns out that Oblivious transfer is necessary and sufficient to obtain multi-party computation for arbitrary functionalities. So I'm not going to go into the details of this because this is not very, the constructions of MPC itself are not very relevant to our work. What we do is build this piece called Oblivious transfer. So in a classical world, like I said, Oblivious transfer is known to imply multi-party computation. And OT itself can be based on the learning with errors, Diffie-Hellman, and a variety of other assumptions that essentially almost any assumption that gives us public key cryptography also gives us oblivious transfer, although the two are not complexity theoretically the same. On the other hand, it is known because of a result of Impagliazzo and Rubik, like I was mentioning before, that one-way functions, when used in a black box way, actually do not imply oblivious transfer. And so this is why the world of mini-crypt as defined by Impagliazzo was different from the world of cryptomania, because in mini-crypt, OT did not exist, and in cryptomania, or in the version of cryptomania, in one version of cryptomania, it did. In a quantum world, on the other hand, oblivious transfer is known to suffice for multi-party quantum computation, like I was mentioning before. And this also follows by a sequence of known works by Killian, and most recently the work of Dulac et al. And on the other hand, the learning with errors assumption is known to imply oblivious transfer in the quantum world. So we already know that if you assume learning with errors, multi-party quantum computation of arbitrary functionalities actually exists. It is also known that one-way functions, and this was because of Krepo-Killian, Bennett, Broussard, Krepo, Skubizevska, and Bowman and Frere, who showed that one-way functions actually imply a weaker form of OT, which is not a full-fledged simulation-based OT like I was talking about, but one that allows for some slight weakenings of these definitions. It turns out, though, that weak OT actually is not in general known to imply standard OT. And again, the main reason is in simulation-based OT, one actually needs to show the existence of a simulator, and weak OT does not actually have such an efficient simulator. And so the question remained, can one-way functions imply the type of OT that suffices for arbitrary MPQC? And sorry, and in the current talk, I'm going to talk about these two works that actually show that it does, that one-way functions do imply OT. So in summary, in a classical world, in a classical setting, when players have access to classical resources and classical communication channels, one-way functions and oblivious transfer are believed to lie in separate worlds. And in fact, there are oracle separations between these worlds. Whereas in a quantum setting, when players have access to quantum resources and quantum communication channels, they're actually the same world. Yeah. One thing that I would like to mention here is that it is unclear that oblivious transfer with quantum communication actually would imply the existence of one-way functions as we define them. And so there is some scope for looking for perhaps weaker assumptions that would be equivalent to all of these things. Would be equivalent to OT and MPQC in particular. Okay, so with that background, let me move on to some of the techniques in these works. All of these make use of the Bennett-Broussard template for quantum key distribution and modify it a certain way to actually obtain oblivious transfer. For background, recall that Bennett-Broussard BB84 states are actually a set of 4 different possible states, each corresponding to a choice of basis and a choice of input. So one could imagine the states 0 and 1 in the computational basis, and then the states plus and minus, which could correspond again to bits 0 and 1 in the Hamiltonian basis. And it turns out that if a state was created in the computational basis, but you measured it in the Hamiltonian basis, this would destroy information about whether the state was a 0 or a 1 in the computational basis. And what you would end up with is a bit 0 with probability half and 1 with probability half. And more generally, given a random BB84 state, if you measure it in the wrong basis, you observe something random. If you measure it in the right basis, you obtain the actual input X that the state was based on. And so what this pattern indicates is that a set of BB84 states, when combined with certain types of crypto, can actually lead to erasure channels. And I'm going to talk now, I'm going to go into more details about why crypto is needed at all if we can already erase things by measuring in the wrong basis. So the OT template of Crepeau Killian and Bennett Broussard Crepeau Skubizewska was as follows. The first step was to establish an erasure channel. And that means there's a sender who has two inputs, S0, S1. Receiver has their private input B. The sender samples bases that are randomly either computational or Hamiltonian, and samples bits that are also randomly zeros and ones. And then it creates a bunch of states by encoding the bit in the basis that they sample. And so this leads to a set of BB84 states that they send to the receiver. The receiver on their side is supposed to sample random bases again. And recall that this is being done to ensure erasures. And we're trying to erase information so that we can securely transfer exactly one of Alice's secrets to Bob and erase the other one. So the receiver samples a set of random bases, which are again either computational or Hamiltonian, and measures the state it received from the sender in these bases to obtain a set of bits. After this point, the sender actually reveals their choice of bases to the receiver. And based on this, the receiver finds out which positions are the ones where theta prime, which is the receiver's basis, matches the sender's basis theta. And so I've marked in green the positions where both basis choices of the sender and the receiver match, and in red the ones where they don't. And we expect that roughly half the positions will match and the other half will not. And so what this results in is the receiver having deleted information about half the X's that the sender was trying to send them and obtained information about the other half. With this, the receiver creates two channels for communication with the sender. The first channel, which corresponds to I sub B, this is a set of positions where the receiver did not obtain erasures. So this channel allows the receiver to learn the secret that the receiver wants to know. And the other channel is the one where the two bases don't match. And here there is some sort of deletion that's going on. Of course, more generally, we won't have it be that exactly half of the bases match and exactly half don't, but it actually suffices to build these two channels where one of them is fully informative and the other has some sort of erasures. And then one can do error correction. Actually, in fact, it suffices to build two channels where one is more informative than the other. And then by an appropriate choice of error correcting code, send and transmit information about over one channel while hiding the other secret. So once the receiver has sampled these two channels, it sends their descriptions to the sender. So since the sender obtains I0 and I1, and actually the sender doesn't know where the receiver's bases did match and where they didn't. And this leads to the receiver's choice bit B being hidden from the sender. So if that makes sense so far, at this point, the sender will build a set of X's corresponding to the set I0. So that means pick X's at positions 3, 4, and 6, which are the bits 1, 0, 1, and call this X0. And then pick, sorry, maybe I did that wrong, but yeah, pick X's at positions 1 to 5, call that the other set, and then send an encoding of both secrets under these X's to the receiver. And now because the receiver knows exactly one of these X's, the receiver can decode exactly one of these Z values that they obtained from the sender. And because the receiver has no clue what the other X is, and actually maybe they even know a few bits of X, but there is some error correction going on here that is under the hood. One can ensure that the receiver is not going to learn the second secret. So This template almost works, except that a malicious receiver can actually cheat. And it can cheat pretty badly. What a malicious receiver can do is it can wait until it obtains the sender's basis choices before measuring. So the receiver was supposed to measure, going back, the receiver was supposed to sample basis theta prime, measure these states in basis theta prime to obtain x prime, and ensure that they had deleted information before obtaining the sender's choice of basis theta. But what a malicious receiver can do is just not measure at this point, wait until they receive theta, and after that, measure all these states in the basis specified by theta. This would help them recover all the x values that the sender was trying to send. And then as a result of this, the receiver would be able to obtain both x0 and x1 and recover both secrets S0, S1. So this is clearly a problem. And to fix this, what was suggested in these works is the following. The receiver actually is supposed to run an extra measurement check subprotocol with the sender that happens before the sender reveals their choice of basis theta. So before obtaining theta, the receiver is supposed to sample basis theta prime and obtain bits x prime, and then commit to the results of these measurements and to the bases that they used while sending a special type of commitment to the sender. The sender then picks a subset of positions and asks the receiver to decommit or to reveal their choices of x prime and theta prime for this set. The sender then obtains openings that consist of the receiver's basis choices and measurement outcomes. And in positions where the receiver's basis choices match the sender's basis choices, the sender checks that the measurement outcomes actually are correct, are what they should have been. Because when the bases match, x and x prime should match, and the sender knows x, and they can check that x and x prime, whether or not x and x prime do match. And here, a commitment, for anyone that is not familiar, a commitment is just a cryptographic primitive, and as the name suggests, it allows the receiver to commit to a certain set of values without actually revealing what they are. So in the commit stage, x primes and theta primes are all hidden, and it's only when the receiver chooses to decommit to some of them that they reveal a subset of x prime and theta prime values. So at this point, this is the measurement check subprotocol. At this point, if the sender is convinced that in positions where theta and theta prime match, x and x prime also match, then the sender and receiver proceed, otherwise they abort. Now, moving forward, the sender and receiver are supposed to discard the positions that were checked. And then with the remaining positions, they continue the same protocol as before, meaning that the sender sends their basis choices to the receiver again creates two channels out of the remaining positions, consisting of positions where theta and theta prime match and where they don't, send descriptions of these channels to the sender, and obtain encodings from them and decode one of them to recover SD. So this is the OT protocol, and it was shown in a work of Damgard et al. That simulation security of this OT protocol follows if the commitments that are being used in the measurement check subprotocol satisfy certain properties. And I will build intuition on what these properties should be by examining the protocol we just discussed. So let's go back to the protocol and note that that it is this commitment that is for which we are going to understand specific properties that it should satisfy. And let's start with security against malicious receivers. So recall that in order to prove security against malicious receivers, one should show the existence of an efficient simulator that extracts the implicit input of the receiver. And so that means the bit B that the receiver was using. One thing that is sometimes confusing to people that have not seen this before is that the existence of this simulator may seem counterintuitive. On the one hand, we're trying to hide the receiver's choice bit in the protocol. And on the other hand, we're saying, well, the simulator needs to be able to extract the bit. So how can the bit both be hidden and be extractable by the simulator at the same time? And the answer is that the simulator is actually allowed access to the receiver's private state, which is not something that other players in the real world are. So for example, a sender would not know what the receiver's choice bit B is because it doesn't have the receiver's private state, but the simulator can actually access this state of the receiver. And so given this state, we want to be able to make it possible for the simulator to extract the bit B. So coming back to the OT protocol, let's imagine a malicious receiver and that's using some implicit choice bit B. The way to actually prove simulation security is to modify this extractable commitment to enable extraction of the X prime and the theta prime values that the receiver was committing to. Now, why is this helpful? Once you're able to extract X prime and theta prime, that allows you to understand which of the channels IB versus IB prime are such that theta matches theta prime in one and not in the other. And in particular, the channel where theta and theta prime all match should be the one that corresponds to the receiver's implicit choice bit. And the other one is one minus the receiver's choice bit. So hopefully the need for extraction in order to allow for simulation is clear. And it turns out that this extractability property of the commitment almost directly implies simulation-based security against malicious receivers. Let me now go ahead and define what exactly does it mean to extract from a commitment. So a commitment, recall, to a bit B is hiding against malicious receivers and is binding against malicious senders, meaning that the committer can only open, once committed, can only open to a particular choice bit. I should mention here that there are many subtleties in building and defining commitments in a quantum setting. I am not going to go into those subtleties for the purpose of this talk, but I invite you to look at both papers for the specific definitions of binding and hiding that we use. I do want to focus on what extractability is. And that essentially says that a committer on input a choice bit B should be able to commit to B in such a way that there should be a simulator that when interacting with any malicious committer should be able to extract an implicit bit B. And this should be such that this is the only thing that the committer can ever open to in the open phase. So this bit is the only possible opening that the committer can provide. Again, there can be computational and statistical versions of this definition, but for the purposes of this talk, I'm not going to go into those details. Okay, so far, hopefully I've convinced you that in order to prove security against malicious receivers, one needs to build extractable bit commitments. Now let's look at security against malicious senders. And again, what Damgard et al. Showed was that simulation security of OT against malicious senders follows if the commitment that was being used, in addition to being extractable for the receivers, for malicious receiver security purposes, was also equivocal. So again, recall that to prove security against a malicious sender in an OT protocol, there should be a simulator that extracts the implicit inputs S0 and S1 from the simulator. And going back to what our OT protocol looks like, let's work backwards. What does one need in order to extract both S0 and S1? Well, we just actually started by looking at an attack the receiver could do if it could somehow not measure at this point. So let me just see if I can, yes. So suppose somehow if the receiver was able to cheat in this measurement check protocol and make it so that they deferred measurements to later, then we said, well, the receiver themselves would be able to learn both S0 and S1. And so what we want the simulator to be able to do is to find a way to commit to something without actually ever measuring all these states. And then when given 2 states to open to, suppose the simulator could measure exactly those 2 states in random basis theta prime and decommit to exactly that set of values without ever having measured any of the other states in this process, then that would allow the simulator, when given theta, to actually measure all of these other states in basis theta. So essentially, the simulator would not be measuring anything at this point, would commit to some junk, and then when given the description of the set S, it would measure exactly states that correspond to set S, leaving states outside the set S untouched, so that at a later point, given theta, the simulator could actually measure states outside the set S in basis theta to obtain all the X values, and as a result, obtain both secrets S0 and S1. And so this is exactly what an equivocal bit commitment would allow you to do. In particular, an equivocal bit commitment has the usual hiding and binding properties, but also satisfies the following. There is a simulator that can actually fool the receiver by not being committing. So what does that mean? The simulator is able to commit to some junk values and later on open them to any bit B of its choice. So it can make this box open to an arbitrary bit B. And so hopefully by this point, I've convinced you that extractability and equivocality are the key properties that we need from these commitments in order to obtain simulation-based security of OT. So the goal going forward is to somehow obtain extractable and equivocal bit commitments from one-way functions. Here I should also mention that these types of commitments are actually known in the classical setting, but because of the difficulties of post-quantum rewinding, they're actually not known from one-way functions in the post-quantum setting. However, we show that with quantum communication, these commitments are actually achievable. And it turns out that equivocal commitments are relatively easier to construct. They involve committing to something and using what are called zero-knowledge proofs. So I'm not going to go into the details of how to build equivocal commitments. What I want to focus on is the more tricky piece, which is building extractable bit commitments. And here, each of these works, each of the 2 works that this talk is about, give 2 different approaches to building extractable bit commitments from one-way functions and quantum communication. So the first approach is essentially inspired by this, by what we just saw. So this is the approach in my joint work with Bartosek, Kola, D'Angelo, and Ma. And this approach is essentially inspired by what we just saw happen in the case of security against malicious senders. So when proving security against malicious senders, recall that we wanted to extract both S0 and S1. And we said an actual receiver participating in this protocol learns exactly one of them, does not learn the other one, but a simulator actually has a way to learn both of them. How would it do that? By deferring measurements and by relying on equivocal commitments to cheat in the measurement check subprotocol. And so this gives us an idea. How about, in order to commit to a message M, let's actually use equivocal commitments, assume they exist. Our goal is to build extractable commitments. And let's just use exactly this template and set the message that we want to commit to be the XOR of S0 and S1. And in a little bit more detail, here's the protocol to commit to a message M. And it's a little bit of a simplification of what I just said. To commit to a message M, the committer sends a bunch of BB84 states as before. Then the committer and receiver run a measurement check subprotocol, where the commitment that they rely on is actually an equivocal commitment only. This commitment does not need to be extractable. And because of equivocality of this commitment, a simulator that interacts with a malicious committer can defer all their measurements to after the measurement check phase and to the point where they receive theta. And given theta, they can recover all the x's. Given all the x's, they can recover the message M. On the other hand, because the receiver, an actual receiver, cannot cheat in this measurement check protocol, because the equivocal commitment is binding against such receivers, it turns out that not the ability to, because a receiver cannot cheat in the measurement check subprotocol, they also cannot recover many of these X values. And as a result, the message M is hidden from an actual receiver, but is extractable by a simulator. So what this really is a way to convert an equivocal commitment to an extractable bit commitment. What we want is actually a single commitment that is both equivocal and extractable. In the paper, we give techniques in order to build such an equivocal and extractable bit commitment from black box use of one-way functions. And it is essentially applying a ZK template and this template one after the other a bunch of times. Again, I'm not going to go into the details of that. That follows relatively straightforwardly. So this is the most interesting conceptual part of the work. Let me now talk about the second approach to building extractable bit commitments. This is in the work of Grillo, Lin, Song, and Vaikunthanathan. And it turns out that, recall that we said that in a quantum world, one-way functions imply weak OT, and it's unclear if they imply oblivious transfer. And their approach shows that weak OT actually does imply extractable and equivocal commitments, which by the Damgard et al. Template already, like I showed you, implies oblivious transfer. And so the new aspect is this link between weak OT and extractable and equivocal commitments. The way that Grillo et al. Do this is they have the receiver send a commitment to 0. And recall again, the goal is to build a bit commitment, which is where the message being committed is hidden from a receiver, but extractable by a simulator. And so what they do is they have the receiver commit to a bit 0, and then send a zero knowledge proof that C is indeed a commitment to 0. If you don't know what a zero knowledge proof is, don't worry about it. This is essentially another cryptographic primitive that allows for a simulator, where the simulator is able to cheat in the proof, but an honest prover, but a cheating prover cannot. So any real world prover cannot cheat, but a simulator can actually prove false statements. So the receiver sends a zero knowledge proof that C is a commitment to 0. And then the committer and receiver execute what is called a conditional disclosure of secrets protocol, which essentially does the following. It obtains some randomness from R and checks if C was a commitment to 1 with randomness R. If it was, it reveals the message M to the receiver, and otherwise the protocol reveals nothing. So for any actual receiver participating in the protocol, note that the receiver, because of the binding of the commitment, cannot actually prove that the commitment is to 0, but then also send to this an opening of the commitment to 1. And that's why the message M is hidden from any actual receivers that participate in this protocol. On the other hand, because a simulator can cheat, like I just said, they can actually send a commitment to 1, give a zero knowledge proof, proving that it's actually a commitment to 0 by cheating, and then execute this protocol where they do actually manage to open this commitment to a 1 and obtain the message M. So that's the super high level idea for how the work of Grillo et al. Builds extractable bit commitments. And so what this is called is a conditional disclosure of secrets protocol. And they show that this can be realized from any weak OT. And in particular, circuit garbling techniques, which is specifically Yao's garbled circuits, and weak OT imply conditional disclosure of secrets. I want to also add that for various technical reasons, it is not sufficient to have the message M only appear as part of this conditional disclosure of secrets protocol. And actually, there needs to be a commitment to the message M that also appears in the transcript. Now, one could do this by simply asking the committer to also commit to M and send this commitment to R, in addition to doing everything else in the protocol. The problem with this is a cheating committer could very well have this message and this other message differ. So these two messages could be completely different, in which case our extraction breaks down, because what the simulator extracts is going to be different from what the committer commits to here. And we don't know if that's correct or wrong. And so in order to fix this, what this work does is they build what is called Verifiable CDS. They say that given the classical transcript of this conditional disclosure of secrets protocol, it is possible to verify that the message M that is revealed by the conditional disclosure of secrets is actually the same as the message M that is being committed here. In order to enable this, one simple thing to do, if this was all entirely classical, was to again attach zero knowledge proofs, try to prove that they're both the same message in zero knowledge so that you don't leak the message. The problem with doing that is that part of this transcript is actually quantum. And so this is fairly non-trivial to do and involves some cut and choose techniques. And in particular, they use garbled circuits, weak OT, cut and choose, and some error correction in order to obtain this primitive that they call verifiable CDS from weak OT. And this seems to be a really interesting primitive that could be useful in other applications where you want to prove things about transcripts that are partially quantum. So with that, I'm running out of time. Let me just move on to open problems and conclude. There's a bunch of really interesting open problems, I think, in this area of what can you do with simple cryptographic assumptions and quantum communication. And we already see a lot of very interesting work on this. So the first general problem is, what does the landscape of cryptographic complexity look like in the presence of quantum communication? And for that, actually, let me just go to the next slide. This is also from Moninar's talk 15 years ago that talked about all these different assumptions that we can put into Cryptomania, which is this public key OT land, and these other assumptions that we can put into Minicrypt. And now what happens to all of these cryptographic primitives and assumptions if one allows for quantum resources? What does this chart look like with quantum communication? A few other open problems. Can we base cryptography with quantum communication on better complexity theoretic foundations than what we're able to base classical cryptography on, which is one-way functions and above? Are there better complexity assumptions that we can use given quantum communication? And of course, we know that we can do QKD information theoretically. So that is completely unconditional, or you may need authentication depending on the model. But what are these complexity theoretic underpinnings of crypto with quantum communication? Another question is, which two-party functionalities are complete for secure computation with quantum communication? So this question has been studied extensively in the classical setting. We have characterizations for almost every functionality we know, whether it is trivial or it implies a certain class of cryptographic primitives, or it implies secure computation in general. So for example, the ability to do AND securely. Alice and Bob can compute the AND of their bits. This implies general purpose classical secure computation. What can we say about general quantum functionalities or even classical functionalities with access to quantum resources? And then finally, can we minimize the number of quantum resources or qubits consumed per OT while still relying only on one-way functions? So in what ways can we optimize these OT protocols? And let's say we are also allowed to use random oracles. What can be done in that set? And so that brings me to the end of this talk. I'm really happy to answer any questions you may have. Thank you.
Okay, thanks a lot, Dakshita, for this very nice talk. I'd like to remind you that if you have any questions for Dakshita, there's the Slack channel, and I invite you to start typing some questions. While we're waiting for, we have one question from Christian Schaffner, and he's asking, how do these approaches from these two papers compare with each other?
Right, great question. So yes, so in fact, I meant to do a slide on that, but I skipped it in the interest of time. So the work, the approach in our joint work with Bartusek, Collet, D'Angelo, and Ma, we make only black box use of one-way functions. That's interesting in a way because in the classical setting, we know that it is impossible to obtain OT from black box use of one-way functions. On the other hand, in order to realize verifiable CDS, the paper of Grillo et al. Makes non-black box use of one-way functions. So that is one difference. Another difference is that the work of Grillo et al. Also obtains a result in the common reference string model that I didn't talk about, but they are able to obtain a constant round OT protocol in the CRS model. And we don't actually talk about the CRS model, and our protocols are all polynomially many rounds. And then a final difference is that we obtain different types of statistical properties. So for example, the extractable commitments that we obtain are statistically hiding. On the other hand, the ones in the work of Grillo et al. Are statistically binding. This confers different types of statistical, so our OT is actually statistically secure against one of the players. On the other hand, their OT is computationally secure against both, but offers some additional binding properties that ours doesn't because it's hiding. So there's just these different flavors of security. But if you restrict to computational security, then both papers achieve at least computational security.
Okay, maybe I'll also ask a question while we wait for more. Do you think there's any chance of being able to prove the reverse implication, like if OT implies one-way functions in the quantum world?
That's a great question. I don't know if it's not even clear to me that that's true. So I would very much like to understand it, but it looks like OT does imply, or can be shown to imply, forms of bit commitment. Bit commitments, whether they imply one-way functions or not, is unclear. We know they are information theoretically impossible, so there is some assumption that we need, but whether that is one-way functions is unclear. The main reason being that classically, all of these primitives imply one-way functions because there's a classical transcript. You can use that to build your one-way function. On the other hand, quantumly, there's quantum operations, quantum states. If you could define some variant of hardness that takes into account these quantum states and quantum operations, then it maybe would imply that, but it is unclear if that would then imply a one-way function. So
thanks. Yeah, it sounds hard. So now we have a few more questions through the Slack. There's Vardan Manga who's asking whether this computational security is through an SDP.
Sorry, could you elaborate on what you mean by SDP?
I'm not sure what they mean either. So I'll just move on to the next question and see if they elaborate. Well, semi-definite programming.
Oh, no. So this is just by reduction to the security of one-way functions. Any adversary that computationally breaks our primitive would break the underlying one-way function. And recall that we can rely on any one-way function in general. So it's not via a specific technique. Yeah.
Okay. Next question. How does all of this fit with the impossibility of quantum bit commitment, oblivious transfer, and multi-party computation, all quantum?
Right. So this shows that complexity-wise quantum bit commitments, or certain forms of them, oblivious transfer and multi-party computation are essentially the same complexity theoretic object. Like they all imply each other. So they're all And here I mean general purpose multi-party computation. Of course, there's some functionalities that you can compute unconditionally, but if you wanted to do every possible functionality, then that class would imply a quantum bit commitment. Now, whether they, which would mean that they are all impossible unconditionally. But yeah, like I was answering Fred's question before, it's unclear if that is equivalent to the existence of one-way functions.
Okay, thanks a lot. One more question. Can you give a broad idea of what the zero-knowledge proof is?
Yes, so it was one of the things I did not actually define in the talk. A zero-knowledge proof is a privacy-preserving proof. It's a way to prove that some NP statement is true. And also for the purposes of the talk, all the zero-knowledge proofs we used were for NP. It's a way to prove that some statement in NP is true without revealing secrets about the statement. And by secrets, I mean specifically the witness. In some more detail, it is a proof that satisfies soundness, meaning that no cheating prover can convince a verifier to accept the proof if the statement is false, except with some small error probability. It also satisfies zero knowledge, which means that for any cheating verifier that tries to gather information from the proof, there's actually a simulator that does not have any of the secrets associated with the statement, and yet manages to produce a view for this verifier that's indistinguishable from their view in an interaction with an honest prover. And so all those technical details aside, what it really means is it's a way to prove a statement without revealing a secret witness about the statement.
Okay, now maybe one last question. Are weak OTs implied by simulatable bit commitments?
So by simulatable bit commitment, if you mean extractable and equivocal bit commitments, then yes. In fact, they imply strong OT, which I'm saying strong, but the simulatable version of OT that I talked about, which does imply weak OT. So
So
okay.
there also, sorry for coming in. So there also what we don't know is whether weak OTs imply one-way functions, basically.
Yeah.
Okay, since I think we've run out of questions on Slack, I'd like to thank Dakshita again for this very nice talk. So I'll give one round of applause for everybody, and got the people in Amsterdam doing the same. And now I think we can. Now there's a break until 4 p.m. and the break is going to happen in the main lobby of the Meet Anyway platform. So I'll see you there.
Yes, indeed. So this concludes this session. You can continue asking questions to Dakshita on the Slack channel. Hopefully she's going to take a look at them and then answer them afterwards. Maybe you can also, if you want to discuss things some more with her, want to have more details on how zero knowledge proofs work or whatever, maybe you can meet up with her in the Meet the Speaker area. I think she hasn't set up things yet, so maybe you want to give her a few minutes before she gets there. And yeah, that was it for now. So I see you in pretty much 20 minutes for the next session then.